Right, so what we're saying is that all vectors can be represented by arrows, like we've got here, and they can be split into two components. So usually, when we say two components, first of all, they must be perpendicular to each other, but but they're usually going to be horizontal and vertical. So if I were to do horizontal and vertical components of this particular one, let's choose red here. Then I would do it like this. That would be my horizontal component. Should be the same height, same width as that one. And that would be my vertical component. Oops. Um, so we can so basically what we do when we split things into components, we're essentially sort of reversing when we add them. So so what we can say about this one here is, in fact, let's just say this is my velocity v. Let's color that in. Oops. Let's color that in black. And then this would be, I guess you could call this Vx, as in the x component of my velocity, and this would be Vy. But of course, let's say that the velocity, the actual velocity, the actual velocity the thing is moving at is equal to 5 meters per second. And let's say that it's moving at an angle to the horizontal of 20 degrees. Would you be able to separate that into, find the horizontal and vertical components of this velocity further? So when we say, so basically these red lines are the sort of essentially the horizontal and vertical story, the part of, so in other words, let's imagine we've got a ball that's actually flying, it's moving at this velocity v, and what would it look like if the ball was being thrown towards you, if it's coming right at you? Well, you wouldn't see the horizontal component because you're looking along that axis. If you were facing that direction, you wouldn't see the horizontal. Apart from you'd see the ball getting slightly larger as it comes towards you, but you would simply see the ball going down because it's falling, right? So you would see it falling down. Now, that the speed at which the ball appears to be falling to you would be Vy, the vertical component, right? So that's what I mean by the vertical component, the speed at which it's falling, because although it's actually going at a diagonal line to the horizontal, 20 degrees, it's true to say that it is both moving along and falling at the same time, the result being that it does this. So we can experience just one of those components by imagining viewing it head on, and you'd only see the vertical components, or maybe viewing it from above. Let's say I'm viewing it from above. Now I can't see whether it's going up or down because of my angle, but I can see it moving horizontally. So if I was viewing it from above, then I would only see Vx, basically. So we can we can then work these components out, and the way that we do that is by using trigonometry. So we would, because if you were to put these back together, Vx, and if we added them like we did before, when we add Vx and Vy, it would make V. Essentially what I'm doing is I'm doing a vector addition, adding vectors. I'm doing it in reverse. I'm splitting it up again. So so in other words, what I'm saying is the actual value of V is equal to Vx plus plus Vy. Okay. We'll try to apply this idea now, and then as time goes on, we'll just sort of eventually take it as read and go, oh, okay, fair enough. That's the way things are. So let's say that the angle is 20 degrees. So we're going to put this into a triangle like this. And we know that this is V, and this is Vx, and this is Vy. The angle is 20 degrees. V is actually equal to 5, and so Vx would be equal to, using trigonometry, Vx would be equal to 5 cos 20, and Vy is equal to 5 sine 20. Okay. So there we go. So this is the two formulae for Vx and Vy. And so we can now work that out by just putting them into our calculator. So I'll just pause the video and do that. So putting them into the calculator, you get 4.7 for the horizontal, 1.7 for the vertical, and that should all work out. And we can double check that we've done this right by using a different method. We can use Pythagoras now. Hopefully, the hypotenuse is equal to the square of each one of those. Hypotenuse, just to remind us about the Pythagoras. Pythagoras named the right angle triangle differently because we're not considering angles. So we've got A, B, and C. Doesn't matter which A and B is, but C is the hypotenuse. A squared plus B squared is equal to C squared. In this case, C is 5. So hopefully, is it true that 5 squared is equal to 4.7 squared? Plus 1.7 squared. If it is, then we've done it right. If it's not, we've done something wrong. So I'll do a question mark there, and we'll just check it out. So using that, we can see it looks about right because 4.7 squared plus 1.7 squared ends up to be roughly 25, which is obviously 5 squared. So we're all good. So yeah, I know that is good, and so we've done everything right. So that would be how to separate something into its components. Now, I said that it doesn't have to be horizontal and vertical. So a standard example when you would not use horizontal and vertical would be this sort of example. We've got a slope. This is a little bit tricky, and we'll do more of this in later lessons. If this becomes a bit... So let's imagine we've got a block on a slope, and what we want to know is this block going to roll down the slope? Is it going to topple? What's it going to do? Now, first of all, we take the center of mass there, and we would calculate the weight. Let's say we know the weight is going to be equal to the mass times the strength of gravity. Now, if we say that, and the angle of the slope we can call theta, for example. Now, using a little bit of trigonometry, which I'm not going to bother proving right now, I will tell you that that angle, in fact, let me just use a different color here. Oh yeah, okay, we'll use a red. That angle is the same angle as that angle, but I'm not going to go into why at the moment. And we've got here two of the forces, which I'm also not going to go too much into, but we've got this force, which I'm just going to call R, and we've got this force here, which I'm actually going to call F. Now, we could separate all of these forces into vertical and horizontal, but it doesn't make much sense because these two are already perpendicular to each other. So it makes more sense to split the weight into that component and that component if we were going to solve this problem. Now, I'm not going to solve that problem because I'm leaping ahead too quickly, but I'm just bring it up to show you that when we split vectors into two components, we don't necessarily need to do it horizontal and vertical. Okay, so